And I'm going to be picking up, despite that being a very short first lecture section, there was a technical difficulty, so I'm going to be splitting the video up a little bit and moving on to the next slide. The transition temperature transition, or TTRS, between two phases, such as between liquid and solid or between ordered and disordered states of a protein, for example, is the temperature at a given pressure at which the molar Gibbs energy of two phases are equal. Above the solid-liquid transition temperature, the liquid phase is thermodynamically more stable. Below it, the solid phase is more stable. For example, at 1 atmosphere, the transition temperature for ice and liquid water is 0 degrees Celsius, and that for gray and white tin is 13 degrees Celsius. At the transition temperature itself, the molar Gibbs energies of the two phases are identical, and there's no tendency for either phase to change into the other. At this temperature, therefore, the two phases are in equilibrium at 0 degrees Celsius, and the two allotropes of tin are in equilibrium at 13 degrees Celsius. As always, when using thermodynamic arguments, it's important to keep in mind the distinction between the spontaneity of a phase transition and its rate. Spontaneity is a tendency, not necessarily an actuality. A phase transition predicted to be spontaneous may occur so slowly as to be unimportant in practice. For instance, at normal temperatures and pressures, the molar Gibbs energy of graphite is 3 kilojoules per mole, lower than that of diamond. So there's a thermodynamic tendency for diamond to convert into graphite. However, this transition to take place, the carbon atoms of diamond must change their location. And because the bonds between the atoms are so strong and the large number of bonds must change simultaneously, this process is immeasurably slow, except for at very high temperatures. In gases and liquids, the mobilities of the molecules normally allow phase transitions to occur more rapidly, but in solids, thermodynamic instability may be frozen in, and a thermodynamic unstable phase may persist for thousands of years. So this brings us back to refresher from Chem 106, where we have our energy versus our reaction progress, where we have our reactant, we have our product, we have our transition, and the delta between the reactant and the product is what determines the favorability of the reaction, but the rate is determined by the delta between the transition to the reactant. And if you have a fairly low barrier in the transition state energetically, the rate of reaction is going to be substantially faster than if you have a very high barrier, which might be insurmountable under practical conditions. So just because the delta exists between the reactant and product, making it favorable, doesn't mean the rate of reaction will be appreciable or even noticeable. Now, let's take a look at phase diagrams. A phase diagram of a substance is a map showing the conditions of temperature and pressure at which its various phases are thermodynamically most stable, as in figure 5.5. For example, in point A in the illustration, the vapor phase of the substance is thermodynamically most stable, but at C, the liquid phase is most stable. So let's take a look at 5.5 for a second. A typical phase diagram showing the regions of pressure and temperature at which each phase is most stable. So on the y-axis we have pressure, and on the x-axis we have temperature. And these lines denote where the solid, liquid, and gas phases are favored at these proportions of pressures and temperatures. The boundaries between regions in a phase diagram are called phase boundaries, and they show the values of pressure and temperature at which two neighboring phases are in equilibrium. So along the phase boundary lines, we have equilibrium processes taking place. So for instance, on this phase boundary between the gas and solid phase, if you had a temperature and pressure laying right on that line, you'd have an equilibrium between solid and gas phases. For example, if the system is arranged to have a pressure and temperature by point B, which we see here, then the liquid and its vapor are in equilibrium, like liquid water and water vapor at 1 atmosphere and 100 degrees Celsius. If the temperature is reduced at constant pressure, the system moves to point C, where the liquid is stable, like water at 1 atmosphere, and the temperature lies anywhere between 0 and 100 degrees Celsius. If the temperature is reduced still further to D, then the solid and liquid phases are in equilibrium, like ice and water at 0, and a further reduction in temperature takes place. The system takes the system into the region where a solid is the most stable phase. So we can consider this green line an isotherm, where we have a fairly stable pressure, even though it's slightly decreasing, and a range of temperatures. And you can see that along these points, this isotherm intersects the phase boundaries, and this leads to the rationale of at which temperature and pressure combination, what phase is preferred. Now, let's talk a little bit about phase boundaries in more detail. The pressure of the vapor in equilibrium with its condensed phase is called the vapor pressure of the substance. Vapor pressure increases with temperature because as temperature is raised, more molecules have sufficient energy to leave their neighbor in that liquid. The liquid-vapor boundary in a phase diagram is a plot of the vapor pressure against temperature. To determine the boundary, we can introduce a liquid into the near vacuum at the top of a mercury barometer and measure by how much the volume is depressed, as we see in figure 5.6. To ensure that the pressure exerted by the vapor is truly the vapor pressure, we have to add enough liquid for some to remain after the vapor forms, for only then are the liquid and vapor phases in equilibrium. We can change the temperature and determine another point on the curve, and so on. And this is how we get a figure 5.7. Now, suppose we have a liquid in a cylinder fitted with a piston. If we apply a pressure greater than the vapor pressure of the liquid, the vapor is eliminated and the piston rests on the surface of the liquid, and the system moves to one of the points in the liquid region of the phase diagram. Only a single phase is present. If instead we reduce the pressure on the system to a value below the vapor pressure, the system moves to one of the points in the vapor region of the diagram. Reducing the pressure will involve pulling out the piston a long way so that all the liquid evaporates. While any liquid is present, the pressure in the system remains constant at the vapor pressure of the liquid because of that equilibrium process existing between the liquid and vapor phases. The same approach can be used to plot the solid vapor boundary, which is a graph of the vapor pressure of a solid against a temperature. The sublimation vapor pressure of a solid, the pressure of the vapor in equilibrium with the solid at a particular temperature, is usually much lower than that of a liquid. A more sophisticated procedure is needed to determine the location of a solid-solid phase boundary, like that between calcite and aragonite, for instance, because the transition between two solid phases is more difficult to detect. One approach is to use thermal analysis, which takes advantage of the heat released during a transition. In a typical thermal analysis experiment, a sample is allowed to cool and then its temperature is monitored. When the transition occurs, energy is released as heat, and the cooling stops until the transition is complete, which is what we see in figure 5.8, where in region D, you get a stabilizing region in change of temperature over time during the transition occurring. The transition temperature is obvious from the shape of the graph, and it is used to mark a point on the phase diagram. The pressure can then be changed and the corresponding transition temperature determined. Any point lying on a phase boundary represents a pressure and temperature at which there's a dynamic equilibrium between two adjacent phases. A state of dynamic equilibrium is one in which a reverse process is taking place at the same rate as the forward process. Although there may be a great deal of activity at a molecular level, there's no net change in the bulk properties or appearance of the sample. For example, any point of liquid vapor boundary represents a state of dynamic equilibrium in which vaporization and condensation occur at matching rates. So you have a forward rate and a reverse rate, and those rates are equal. Therefore, the bulk of the system is not changing, despite there being an enormous amount of forward and reverse motion happening simultaneously. Molecules are leaving the surface of the liquid at a certain rate, and molecules already in the gas phase are returning to the liquid at the same rate. As a result, there's no net change in the number of molecules in the vapor, and hence no change in its pressure. Similarly, a point on the solid-liquid curve represents conditions of pressure and temperature at which molecules are ceaselessly breaking away from the surface of a solid and contributing to the liquid. However, they're doing so at a rate that exactly matches that at which the molecules already in the liquid are settling onto the surface of the solid and contributing to the solid phase. Now, moving along to the location of phase boundaries. Thermodynamics provides us with a way of predicting the location of the phase boundaries. Suppose two phases are in equilibrium at a given pressure and temperature. Then, if we change the pressure, we must adjust the temperature to a different value to ensure that the two phases remain in equilibrium. In other words, there must be a relation between the change in pressure, delta P, that we exert and the change in temperature, delta T, we must make to ensure that the two phases remain in equilibrium. We show in derivation 5.4 in the text that the relation between the change in temperature and the change in pressure needed to maintain equilibrium is given by the Clapeyron equation, shown as figure 5.5a. The Clapeyron equation 5.5a shows delta P equals the change in transition enthalpy over temperature times the change in transition volume as a term times the change in temperature for the process, where delta transition H is the enthalpy of transition and delta transition V is the volume of transition, or the change in molar volume when the transition occurs. This form of the Clapeyron equation is valid for small changes in pressure and temperature, because only then can delta transition H and delta transition V be taken as constant across that range. The Clapeyron equation tells us the slope, the value delta P over delta T, of any phase boundary in terms of the enthalpy and volume of transitions. For solid-liquid phase boundary, the enthalpy of transition is the enthalpy of fusion, which is positive because melting is always endothermic. For most substances, the molar volume increases slightly in melting, so delta transition volume is positive but small. It follows that the slope of the phase boundary is large and positive, up from left to right, and therefore that a large increase in pressure brings about only a small increase in melting temperature. Water, though, is quite different, for although its melting is endothermic, its molar volume decreases on melting. Liquid water is denser than ice, thankfully, which is why it floats. So delta transition volume is small but negative. Consequently, the slope of the ice-water phase boundary is steep but negative, down from left to right. Now, a large increase in pressure brings about a small lowering of the melting temperature of ice. We cannot use equation 5.5 to discuss the liquid-vapor barrier boundary, except over very small ranges of temperature and pressure, because we cannot assume that the volume of the vapor and therefore the volume of the transition is independent of pressure. However, if we suppose that the vapor behaves as a perfect gas, then it turns out, based on derivation 5.5, that the relation between a change in pressure and a change in temperature is given by the Clausius-Clapeyron equation, which is what follows in equation 5.6 here, where we've got a little bit of a modification to what we saw before. We're still looking at delta P, but it's transformed with the natural log. We still have a change in vapor enthalpy. We also still have a delta T, and we're still looking at temperature, but now it's squared, and we have our ideal gas law term. So the Clausius-Clapeyron equation is an approximate equation for the slope of a plot of the logarithm of vapor pressure against temperature. So if you rearrange it, we can see that the vapor pressure P prime at temperature T prime is related to the vapor pressure P at temperature T. This gives us the following relationship, which gives us a Y equals mx plus b style linearization that we can plot, where we have y and then mxb. And that is incredibly useful because we can see this in figure 510. Clausius-Clapeyron equation gives us the slope of a plot of a logarithm of the vapor pressure of a substance against the temperature. The slope at a given temperature is proportional to the enthalpy of vaporization of the substance. So this term here actually gives us a really nice slope term at any single point. Equation 5.6 shows us that the temperature of a liquid is raised as vapor pressure increases. Equation 5.7 lets us calculate the vapor pressure at one temperature provided we know it at another temperature. The equation tells us that for a given change in temperature, the larger the enthalpy of vaporization, the greater the change in vapor pressure. The vapor pressure of water, for instance, responds more sharply to a change in temperature than that of benzene. Note, too, that we can write equation 5.7 as follows. Then, because natural log of x equals natural log 10 times log of x, we can derive the following expression. And this expression has the form of log p equals a minus b over t, where a and b are constants, and the value of a depends on the unit adopted for p. This is the form in which the vapor pressures are commonly reported. And we see that in table 5.1 and figure 5.11, which I have included off to the side here. So in table 5.1, we have our a term and b over k term over different temperature ranges that are approved. So a brief illustration of this: a vapor pressure of benzene in the range of 0 to 42 degrees Celsius can be expressed in the form of equation 5.8. And this is fairly straightforward. It's identifying terms to substitute from the table. A good note on practice: you'll sometimes see equation 5.8 written out without units or with the units in parentheses. It's much better practice to include the units in such a way as to make all of the quantities unitless. So that's a best practice, as always, to include units unless you have a truly unitless constant. So, characteristic points. As we've seen, as the temperature of a liquid is raised, its vapor pressure increases. First, consider that we would observe what we would observe when we heat a liquid in an open vessel. At a certain temperature, the vapor pressure becomes equal to the external pressure, and at this temperature, the vapor can drive back the surrounding atmosphere and expand indefinitely. Moreover, because there's no constraint on expansion, bubbles of vapor can form throughout the body of the liquid, a condition known as boiling. The temperature at which the vapor pressure of a liquid is equal to the external pressure is called the boiling temperature. When the external pressure is 1 atmosphere, the boiling temperature is called normal boiling point, or T sub B. It follows that we can predict the normal boiling point of a liquid by noting the temperature on the phase diagram at which its vapor pressure is 1 atmosphere. The use of 1 atmosphere is the definition of normal boiling point rather than 1 bar, based on historical reasons. The boiling temperature at 1 bar is called the standard boiling point. and they're incredibly similar because a bar is very similar to an atmosphere. Now, consider what happens when we heat the liquid in a closed vessel. Because the vapor cannot escape, its density increases as the vapor rises, and in due course the density of the vapor becomes equal to that of the remaining liquid. At this stage, the surface between the two phases disappears, as was predicted in figure 114. The temperature at which the surface disappears is the critical temperature, T sub C, which we first encountered in section 1.1. The vapor pressure at the critical temperature is called the critical pressure, and the critical temperature and critical pressure together identify the critical point for a substance. If we exert pressure on a sample that is above its critical temperature, we produce a denser fluid. However, no surface appears to separate the two parts of the sample, and a single uniform phase, a supercritical fluid, continues to fill the container. That is, we have to conclude that a liquid cannot be produced by the application of pressure to a substance if it is at or above its critical temperature. That is why the liquid-vapor boundary in a phase diagram terminates at the critical point. Table 5.2 actually shows a sequence of critical constants associated with different compounds. The temperature at which the liquid and solid phase of a substance coexist in equilibrium at a specified pressure is called the melting temperature of the substance. Because a substance melts at the same temperature as it freezes, melting temperature is synonymous with freezing temperature. The solid-liquid boundary, therefore, shows how the melting temperature of a solid varies with pressure. The melting temperature, when the pressure on a sample is 1 atmosphere, is called the normal melting point, or the normal freezing point, T sub F. A liquid freezes when the energy of the molecules in liquid is so low that they cannot escape from the attractive forces of their neighbors and they lose their mobility. There's a set of conditions under which 3 different phases, typically solid, liquid, and vapor, are simultaneously coexisting in equilibrium. It's represented by the triple point, where the 3 phase boundaries meet. All those 3 phase boundaries meeting right here we see in figure 5.12. The triple point of a pure substance is a characteristic, unchangeable physical property of the substance. For water, the triple point lies at 273.16 Kelvin and 611 pascals, and ice, liquid water, and water vapor coexist in equilibrium at no other combination of pressure and temperature. At the triple point, the rates of each forward and reverse process are equal, but the 3 individual rates are not necessarily the same, because the quantities can be different in these equilibriums. The triple point and the critical point are important features of a substance because they act as frontier posts for the existence of liquid phase. As we see from figure 513a, if the slope of the solid-liquid phase boundary is as shown in the diagram, over here 513a, the triple point marks the lowest temperature at which a liquid can exist. The critical point also marks the highest temperature at which the liquid can exist. So we shall see in the following section that for a few materials, most notably water, the solid-liquid phase boundary slopes in the opposite direction, and then only the second of the conclusions is relevant. So let's take a look at 513 in a little bit more detail here, where on the y-axis we have pressure, and on the x-axis we have temperature, and we have our standard phase diagrams. In A, we see for substances that have phase diagrams resembling the one shown in A, which is common for most substances with the important exception of water, the triple point and the critical point mark the range of temperatures over which the substance may exist as a liquid. The shaded areas show the region of temperature in which a liquid cannot exist as a stable phase. But in B, a liquid cannot exist as a stable phase if the pressure is below that of the triple point for normal or anomalous liquids. So Let's do a little quick segue into supercritical fluids. Supercritical carbon dioxide is the center of attention for an increasing number of solvent-based processes. The critical temperature of 304.2 Kelvin and pressure of 72.9 atmosphere are readily accessible, and carbon dioxide is cheap. The mass density of supercritical CO2 at its critical point is 0.45 grams per cubic centimeter. However, the transport properties of any supercritical fluid depend strongly on its density, which in turn is sensitive to the pressure and temperature. For instance, densities may be adjusted from gas-like to liquid-like. A useful rule of thumb is that the solubility of a solute is an exponential function of the density of the supercritical fluid, so small increases in pressure, particularly close to the critical point, can have very large effects on the solubility. In effect, you have a tunable solvent. A great advantage of supercritical CO2 is there's no noxious residue once the solvent has been allowed to evaporate. So, coupled with its low critical temperature, supercritical CO2 is ideally suited for food processing and the production of pharmaceuticals. It's used, for instance, to remove caffeine from coffee. The supercritical fluid is also increasingly being used for dry cleaning, which avoids the use of carcinogenic and environmentally deleterious chlorinated hydrocarbons. Supercritical CO2 has been used since the 1960s as a mobile phase in superfluid chromatography, but it fell out of favor when a more convenient technique of high-performance liquid chromatography was introduced. However, interest in supercritical fluid chromatography has returned, and there are separations possible in SFC that cannot easily be achieved through HPLC, such as the separation of lipids of a phospholipid. Samples as small as 1 picogram can be analyzed. That's a very, very low quantity. The essential advantage of SFC is that diffusion coefficients in supercritical fluids are an order of magnitude greater than in liquid, so there's less resistance to the transfer of solutes through the column, with the result that separations may be effected rapidly or with high resolution. The principal problem with supercritical CO2, though, is that the fluid is not a very good solvent, and the surfactants are needed to introduce many potentially interesting solutes to dissolve. Supercritical CO2-based dry cleaning depends on the availability of cheap surfactants, so too does the use of supercritical CO2 as a solvent for homogeneous catalysts such as metal complexes. There appear to be two principal approaches to solving the solubilization problem. One solution is to use fluorinated and siloxane-based polymeric stabilizers, which allow polymerization reactions to proceed in supercritical CO2. The disadvantage of these stabilizers for commercial use is their great expense. An alternative and much cheaper approach is polyether carbonate copolymers. The copolymers can be made more soluble in supercritical CO2 by adjusting the ratio of ether and carbonate groups. The critical temperature of water is 374 degrees Celsius, and its pressure is 218 atmospheres. The conditions for using supercritical water are therefore much more demanding than supercritical CO2, and the properties of the fluid are highly sensitive to pressure. Thus, as the density of supercritical water decreases, the characteristics of a solution change from those of an aqueous solution through those of a non-aqueous solution, and eventually to those of a gaseous solution. One consequence is that reaction mechanisms may change from ionic to radical. Very interesting content on supercritical fluids. Moving along, back to the nitty-gritty, phase rule. You might wonder whether 4 phases of a single substance could ever be in equilibrium, such as 2 solid forms of tin, liquid tin, and tin vapor. To explore this question, we think about the thermodynamic criterion for 4 phases to be in equilibrium. For equilibrium, 4 molar Gibbs energies would all have to be equal, and we could write the following, where GM1 equals GM2, GM2 equals GM3, GM3 equals GM4. The other equalities, GM1 equals GM4, and so on, are implicit in these 3 equations. Each Gibbs energy is a function of the pressure and temperature, so we should think of these 3 relations as 3 equations for 2 unknowns, P and T. In general, three equations for two unknowns have no solution. For instance, the three equations 5x plus 3y equals 4, 2x plus 6y equals 5, and even x plus y equals 1 have no solution. Therefore, we have to conclude that the four molar Gibbs energies cannot all be equal. In other words, four phases of a single substance cannot coexist in mutual equilibrium. The conclusion we have reached is a special case of one of the most elegant results of chemical thermodynamics. The phase rule was derived by Gibbs and states that for a system at equilibrium, F equals C minus P plus 2, where F is the number of degrees of freedom, C is the number of components, P is the number of phases. The number of components C in a system is the minimum number of independent species necessary to define the composition of all the phases present in the system. The definition is easy to apply when the species present in a system do not react, for then we simply count their number. For instance, pure water is a one-component system, and a mixture of ethanol and water is a two-component system where C would equal 2. The number of degrees of freedom, F, of a system is the number of intensive variables such as pressure, temperature, and mole fractions that are independent of the amount of material sample that can be changed independently without disturbing the number of phases in equilibrium. For a one-component system, such as pure water, we can set C equals 1, component equals 1, and the phase rule simplifies to F equals 3 minus P. When only one phase is present, F equals 2, which implies that P and T can be varied independently. In other words, a single phase is represented by an area on a phase diagram. When two phases are in equilibrium, F equals 1, which implies that pressure is not freely variable if we have a set temperature. That is, the equilibrium of two phases is represented by a line in the phase diagram. A line in a graph shows how one variable must change if another variable is varied inherently, and we see this in figure 5.14. Instead of selecting the temperature, we can select the pressure, but having done so, the two phases come into equilibrium at a single definite temperature. Therefore, freezing, or any other phase transition for a single substance, occurs at a definite temperature and a given pressure. When three phases are in equilibrium, F equals 0. The special invariant condition can therefore be established only at a definite temperature and pressure, where we have a single definite temperature and pressure defining the equilibrium between the three phases. This special invariant condition can therefore be established only at definite temperature and pressure. The equilibrium of three phases is therefore represented by a point, the triple point on the phase diagram. If we set P equal 4, we get the absurd result that F is negative. And that result is in accord with the conclusion at the start of the section that four phases cannot be in equilibrium in a one-component system. So, what about phase diagrams of typical materials? We shall now see that these general features appear in phase diagrams of a selection of pure substances. Figure 5.15 below is the phase diagram for water. The liquid-vapor phase boundary shows how the vapor pressure of liquid water varies with temperature. We can use this curve, which is shown in more detail in figure 5.7, to decide how the boiling temperature varies with changing external pressure. For example, when the external pressure is 19.9 kilopascals at an altitude of 12 kilometers, water boils at 60 degrees Celsius because that's the temperature at which the vapor pressure is 19.9 kilopascals. The solid-liquid boundary line in figure 5.15, which is shown in more detail in 5.16, off to the right here, shows how the melting temperature of water depends on pressure. For example, although ice melts at 0 degrees Celsius at 1 atmosphere, it melts at -1 when the pressure is 130 bar. The very steep slope of the boundary indicates that enormous pressures are needed to bring about significant changes. Notice that the line slopes down from left to right, which, as we anticipated, means that the melting temperature of ice falls as pressure is raised. As pointed out in section 5.5, we can trace the reason for this unusual behavior to the decrease in volume that occurs when ice melts. It's favorable for solid to transform into denser liquid as the pressure is raised. The decrease in volume is a result of the very open structure of the crystal structure of ice. Figure 5.15 shows that water has many different solid phases other than ordinary ice. Ice, I, shown in figure 5.17, which we'll get onto the next page. These solid phases differ in the arrangement of water molecules. Under the influence of very high pressures, hydrogen bonds buckle, and the H2O molecules adopt different arrangements. These polymorphs, or different solid phases of ice, may be responsible for the advance of glaciers, for ice at the bottom of glaciers experiences very high pressures where it rests on jagged rocks. The sudden apparent explosion of Halley's Comet in 1991 may have been due to the conversion of one form of ice into another in its interior. Figure 5.18 shows the phase diagram for carbon dioxide. The features to notice include the slope of the solid-liquid boundary. The positive slope is typical of almost all substances. The slope indicates that the melting temperature of solid carbon dioxide rises as pressure is increased. As the triple point, 217 Kelvin, 5.11 bar, lies well above ordinary atmospheric pressure, liquid carbon dioxide does not exist at normal atmospheric pressures, whatever the temperature, and the solid sublimes when left in the open, hence the name dry ice. To obtain liquid carbon dioxide, it's necessary to exert a pressure of at least 5.11 bar on the system. Cylinders of carbon dioxide generally contain the liquid or compressed gas. If both gas and liquid are present inside the cylinder, then at 20 degrees Celsius, the pressure must be 65 atmospheres. When the gas squirts through the throttle, it cools by Joule-Thomson effect, so when it emerges into a region where the pressure is only 1 atmosphere, it condenses into a finely divided, snow-like solid. Figure 5.19, to the right, shows the phase diagram for helium. Helium behaves unusually at low temperatures. For instance, the solid and gas phase of helium are never in equilibrium, however low the temperature. The atoms are so light that they vibrate with a large amplitude motion even at very low temperatures, and the solid simply shakes itself apart. Solid helium can be obtained, but only by holding the atoms together by applying pressure. A second unique feature of helium is that pure helium-4 has 2 liquid phases. The phase marked helium-1 in the diagram behaves like a normal liquid. The other phase, helium-2, is a superfluid. It is so called because it flows without viscosity. Helium is the only known substance of liquid-liquid boundary in its phase diagram, although recent work has suggested that water may have a superfluid liquid phase as well. And wrapping up, a short slide on the molecular structure of liquids. One question that should arise in your mind is the molecular basis of the materials we've been discussing, and in particular the molecular nature of pure liquid phase. That is, the questions we address here. The starting point for the discussion of gases is the totally random distribution of molecules of a perfect gas. The starting point for the discussion of solids is the well-ordered structure of perfect crystals. The liquid state is between these extremes. There's some structure and some disorder. The particles of a liquid are held together by intermolecular forces of the kind we discussed in chapter 15 later, but their kinetic energies are comparable to the potential energies. As a result, although the molecules are not free to escape completely from the bulk, the whole structure is very mobile. The flow of molecules is like a crowd of spectators leaving a stadium, for instance. In a crystal, particles lie at a definite location in the absence of defects of thermal motion. This regularity continues out to large distances to the edge of the crystal, billions of molecules away. So we say that crystals have long-range order. When the crystal melts, the long-range order is lost, and whenever we look at long distances from a given particle, there's equal probability of finding a second particle. Close to the first particle, though, there may be a remnant of order. Its nearest neighbor might still adopt approximately their original position, and even if they're displaced by newcomers, the new particles might adopt their vacated positions. The existence of this short-range order is due largely to intermolecular forces that exert their influence over short distances. For example, in liquid water, any given water molecule is surrounded by other molecules at the corners of a tetrahedron, similar to the arrangements of ice. The intramolecular forces, in this case largely hydrogen bonds, are strong enough to affect local structure right up to the boiling point. And that's going to be it for Chapter 5. I'll be loading this video for everyone to view, and we'll be coming up with a lecture on Chapter 6 in the near future.